Welcome back. Now that we have seen all kinds of different ways to do text representation, let's get into some tasks that you can actually solve with it. So let's get into the topic of natural language processing tasks. We will today be talking about topic modeling, sentiment analysis, named entity recognition, as well as entity linking. Now let's get into it. So, we saw embeddings, which are a vector space model type of deal for text representation, but we also have something called topic modeling, in which you get something that's kind of similar to embeddings, but oftentimes on a lower dimension. Namely, what we try to do is that we try to figure out what is the text about. We use a lot of data, try to create a topic model, and then whichever document we get in is then considered to be a combination of different topics, because all words are associated to different topics, different amounts, and as such, when you use them, you get a distribution over the different topics for each document. So in topic modeling, we generate topics, which are latent structures, and we describe documents as parts of these said topics. Why is this useful? Well, it's useful because it's oftentimes used to just discover some hidden topics or some kind of implicit relations between data. And it can also help to summarize documents, among others. So, as I alluded to before, we use input data. We use some form of, let's see, can I change my cursor again? Laser pointer, there we go. So we use all kinds of different input documents. For instance, we could be using all kinds of books from a library and then try to generate all kinds of topics. Here on the left, we have an example of these kinds of topics where each line is supposed to represent one topic. For instance, you can here see human, Plato, Socrates, universe, philosophical, mind, ethics. This is sounding very, well, philosophical. Overall, that the words here all suit, well, it sounds more like the ancient Greek philosophers type of direction. Whereas here, if we go for topic 4, you might have ships, fleet, sea, shore, admiral, vessels, land, boats, admiral. Well, here you see that's apparently case sensitive. In this case, was you have capital A admiral and lowercase admiral in there, but that these are all kinds of words linked to boats and to, well, the sea. So all kinds of naval things in there. So the idea is that we can just take descriptions. We could also just take summaries and try to categorize them just to say what people are talking about. And then afterwards, when we look at different words, we can see at how they score on different topics. So for instance, you can here see how important, this is just an example of 12 different topics where you see kind of the scores for ensign, sept, gent, November, redan, and how high the scores are within each topic for them. But let's have a look. Like, topic modeling is interesting, but there's a few variables that come into play there, which can pose a challenge. Namely, how many latent topics do you want to have? That's always debatable. Like, because technically you could create just one topic, which I guess you could just label it as the world or text, because then you'd have everything in it. Or you can do pretty much a new topic for each document. Let's assume we have a million documents. There's probably more that people oftentimes use. But like, let's say there's a million documents. And we could also say that, hey, there's then a million topics. But that's kind of beside the point, because it wouldn't help us at all. So we have these kinds of bounds of, okay, at what point is it still useful to have this denomination of this is a specific topic? Further, another challenge in this domain is that topics are generally unlabeled. The topic tends to be a latent representation, and you can have certain topic words that are within a given topic, but then how do you label this? Well, a simple way would be, for instance, to ask a language model, hey, can you tell me what's in common for all of these words? But that would kind of be a baseline. Yes, and then where do you do the segmentation for a topic within a document? Like, where does one topic start and the other one end? Where does one topic end and the other one start, rather? And yes, so now we'll have a look at an approach on how you can do topic modeling, which is nowadays a state-of-the-art approach from, I think it's 2023. So far, it's called Top2Vec. So, how does Top2Vec actually work? Top2Vec, it works in 5 steps. The first one is that, hey, let's create jointly embedded document and word vectors, which in practice, they use Doc2Vec. I'm assuming hence the Top2Vec name that's inspired by Word2Vec, Doc2Vec, and so on. But they also do make use of BERT embeddings, on the other hand. And here we can see in this nice illustration that you can have words and documents within the same space, so that this further accentuates that, okay, this word or this document is very close to this word and such. For instance, here we see deep learning is a subset of machine learning, blah, 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 from data that is unstructured and unlabeled. So here we see what are the actual important words and how are, because that's the idea, that the documents get closer to the most important words within the documents. Next, we then want to lower the dimensionality of the embeddings. So embeddings can be high dimensional, such as, I think the ones we saw before were 512 dimensions, and that's kind of hard because some of the newer topic modeling approaches tend to use clustering algorithms, and they tend to suffer from the curse of dimensionality. So a very common way of doing it, a very common way of circumventing that is to actually just reduce the dimensionality as much as you can, and then hope that the clustering algorithms work well. So what they do here is in step 2, they use UMAP, which is used for dimensionality reduction, and then you get the document vectors. And in the step 3, they then apply a clustering algorithm by the name of HDBScan. Well, HDBScan is a density-based clustering algorithm, and the advantage of it is that it also automatically tells you, well, one of the advantages of it is that it automatically tells you the number of clusters. So it's not an input parameter. So for the topics, it can also just tell you how many topics there are then in the end. Here we see for the clustering in the different colors here. Here on the right is a 2D projection of these clouds of vectors, which I'm assuming originally they're in a way higher dimensional space, but I'm assuming it was a 3D figure that you can go around. So you see yellow here, for instance, they're all together, and then orange and such. Now then, step 4, after they've completed the clustering part, they then just compute the average of, well, of the documents within the topic, and ta-da, this is our topic vector. This is what will represent now this topic. And HGB scan also has the advantage that it also finds outliers pretty well. That's parameter based as well, but it can figure out what's an outlier for this here, and they make use of it here as well. So once we have the topic vector, what we can do is just check for nearest neighbors, and voila, we now have our topic. We see that, for instance, for this topic here, we have global climate warming, change, temperature, and carbon together, which does seem to make a lot of sense, that it's a topic about climate change mainly, or, well, about climate in general, I assume. Now then, that's it for Top2Vec. And there is a different approach that I'll show very shortly. It's called bird topic. It's relatively similar from the idea as Top2Vec, with a bit of a difference towards the end, but they also use embeddings. They use sentence bird, which is a sentence transformer based on bird, then apply dimensionality reduction, also UMAP. They also apply HGB scan of clustering, but then in the end, they then extract the topics via so-called class-based TF-IDF. And Top2Vec and bird topic together kind of form the state of the art right now in this field. Moving on to the next topic. The next topic is sentiment analysis. So the idea in this task is we want to figure out, okay, how does the writer feel in this text passage? And so, for instance, we have our text that we had before as well, with someone having just landed in Tokyo. And okay, how do they feel? Are they happy? Are they sad? Are they conflicted? There's all kinds of different classes of emotions that might be analyzed on or classified into. Or, for instance, here, for instance, here in this review, where we have someone who wrote Dr. Lewis saved my life, but then just gave them 4 stars. So, which is kind of funny in that regard, considering the circumstances. And so sentiment analysis in practice can be useful for, well, in an automated fashion, checking on reviews, for instance, or to detect the controversy, or to have just some general contextual awareness, honestly. And there's some challenges in these approaches. Like in this task radar, for instance, there's ambiguity in language, which is oftentimes an issue. But particularly irony or sarcasm, if someone writes great, it can be a very sarcastic comment, or it can be actually heartfelt. And that's kind of hard to detect in sentiment analysis unless we use other kinds of information from around. Like contextual awareness can be very, very important here. Now then, this is just generally the task of sentiment analysis, but there's a bunch of different approaches going at it. If you just base it on keywords, this is what we call a more lexicon-based approach, where we have different words that work well, or that don't work well, but they are very prone to, for instance, sarcasm and that kind of stuff. And so yeah, you have this dictionary approach, where you have statistical and semantic approaches, corpus-based, and this is just so you see a kind of more general overview of what's actually happening. But as in most areas of natural language processing or text mining nowadays, transformer networks tend to also tend to reign supreme. Now then, moving on. So we started in the beginning with unstructured data. So that's unfortunate because unstructured data creates quite a few issues that we try to solve despite it. We tend to try to extract data from unstructured documents, but it's pretty hard, especially to get right every time. It's pretty hard, despite using highly complex machine learning algorithms. And well, so what if we do it right? We might want to just persist our findings so that we can reuse them. So the idea behind, so that's the idea behind knowledge graph, mainly that we want to persist our knowledge and what we figure out so that we can actually reuse this knowledge and perhaps even deduce more things based on it. So the idea behind knowledge graphs is that we want to find a reusable and queryable way to structure all of the data, which in the end led to knowledge graphs. So contextually, for so-called knowledge graphs, the idea is that all information is stored in so-called triples, which are statements or facts made up of three parts, namely a subject, a predicate, and an object. And yeah, we want to, I'm not going to go into particular depth here, but there's also a query language that was specifically designed for knowledge graphs. The query language is called SPARQL, close to SQL, as you might notice. And here's a sample query for it. For instance, there's a query where we just want to count for the distinct C's, a CT block collection. Here we see that the question mark designates a variable, which here in this case is a subject. Is a predicate, and A of B MD system is an object. And then we continue here. We see, okay, we see S is a system, and we want R to connect to S, to the aforementioned S, with A of B off system, and so on. So there are certain links that we're creating here, certain jumps, as you may have it, in a knowledge graph. So there are some general purpose knowledge graphs out there, which are pretty cool. For instance, DBpedia, which is based on Wikipedia largely, and it's mainly rule-based, how it's generated. And there's like 400 million facts in it. And here on the right, we have a visualization of a subgraph of it, because it's very hard to actually visualize certain things, knowledge graphs, effectively in a full fashion. But here we have a certain subgraph where we have mostly music, I assume, because we have jazz, pop, hip hop, rock, folk, and then we see the interconnections, how they're connected to each other generally. And yeah, the more connections there are, the bigger the node is, I assume, in this case. So Wikipedia with 400 million facts already sounds like a lot, but there's Wikidata that has 12 billion facts, which is 30 times the amount in Wikipedia, if my math is correct. But then even larger than that, the Google Knowledge Graph is supposed, as far as we know, has about 500 billion facts in it, which is even greater. And it's oftentimes used for those little info boxes that you have on the right when you Google something. Another kind of relatively famous example of knowledge graphs is the Amazon product knowledge graph, where they store most of the products and where you can query it like a search engine indirectly. And yes, those are the most notable examples that are out there. There's quite a few, but well, not that many, but they're relatively large and they're pretty interesting, honestly. Now, this is all well and good, looks nice, interesting. But now for our example of before, where we had an input text about Tokyo and, well, tourism in Japan, I assume. How could we represent this as a knowledge graph? Well, this is one example on how it could be done. We could have some. Okay, I noticed that I still left a picture of a wrestler up here. Yes, so this is a sample knowledge graph where we have for the text Tokyo. Well, Tokyo can mean different things. It can be the city. There's a movie that's called Tokyo, and there's a song, or multiple even. So in a knowledge graph, we can store all kinds of information. We can store this level of information here that's entities, as we may call them. They're a resource within a knowledge graph, and an entity can be of a certain type. Like an entity can be connected to a different entity in different kinds of ways, but an entity also has a certain type that can be attributed to it oftentimes. Well, should actually be every time, now that I think of it. And for the city of Tokyo, it can have the type of city, and city is a type of settlement, which is a type of location. The location is a type of thing. So there's a kind of hierarchy going on here that, okay, you have a movie, like Tokyo Film, it's a movie, which is a kind of work, and work is a thing. The idea is that everything is a thing within a knowledge graph, and this is what we refer to here as more implicit knowledge, where we can actually deduce things to a certain degree by having interconnections, and this is where so-called ontologies also come in. And there are lectures for that at KIT that I would recommend going to because it's very interesting for storing knowledge and actually making use of that implicit knowledge as well as the more explicit one with the entities. Now then, as you see here, I wrote them all down relatively nicely with thing, work, but in practice, all of these words here are represented by so-called URIs. Here we see, for instance, w3.org/so-and-so OWL thing. So that's all of these here on top are more based in the ontologies because they're more the concept of a place, the concept of a settlement, the concept of a city, and it's more there for a type hierarchy to say that, hey, we have an entity here that is of a certain type, that is a city, that is a movie, that is a song and such, or sushi is food, or sushi can also be the wrestler Akira Raijin. Sorry for my pronunciation. But yes, so oftentimes it's just simplified, as we saw before, by the actual words when it's presented to someone. Well then, knowledge graphs. Cool. They are still relevant nowadays. Like, it's not a recent concept. It's been there for a while. The idea was that knowledge graphs would help us get really far to have the web of data just be very nicely structured so we can actually address everything in a very explicit fashion. Unfortunately, we're not quite there yet. For some things we are, for other things not quite. But knowledge graphs are still being used nowadays for more modern AI approaches. among others, for more recent RAG approaches, but there's also some people from Wiki Research that are doing interesting stuff with it, where they're actually querying from Wikidata, checking what the responses are, and then combining that with LLMs. And yes, that's pretty cool. So, moving on to the next task. The next task we're looking at is called named entity recognition. So the idea for named entity recognition is that we want to link text to types. Again, taking our sub-example from before with Tokyo and sushi from the sentence before, we want to link, we want to figure out what types of entities these are. Like, want to know that Tokyo represents the city, or that sushi is a kind of food. And there are named entity recognition approaches that work, among others, most of them nowadays work based on machine learning. Some of them work on more simpler statistical approaches, but that just directly from the sentence structure can tell you, okay, Tokyo is a place or is a city. So it's this upper part here that we're trying to recommend or try to classify on for text in theory. In practice for any R, we tend to just use fewer types. There are fine-grained approaches, but the most common types tend to be person, location, organization, time, quantity, or other. If your system discovers, okay, this is a named entity, but I don't know what kind. So the idea is here we have our text and we want to identify named entities within this text and annotate them with a set of types. Technically, you could also apply multiple types for one entity, but that's usually not very much applied in reality because, okay, Tokyo being a location and a person would be a bit weird. Somehow technically possible, because you could say, oh, it's a moving location because the person is moving around, but that's a bit more wonky. So people are still trying to work on, let's say, this more basic approach to it. So the idea is we have this input text. Now then we want to identify named entities within this text. We've done that now. We've somehow figured out that Tokyo, temples, cherry blossom, sushi spots, hotel, Tokyo, and too long apparently count as named entities for us. Well, then we found that, oh, Tokyo, that's a location. Temples is a location. Cherry blossoms, also a location. Same for sushi spots because it's a place. Then the hotel is also a place, and so on. And then we just figured these kinds of out, and we just annotated with it. And that's kind of the NER process. How does NER systems work? But there's different approaches to actually fulfilling this. Now then, we have NER. What could we want to do next? The next task we'll be looking at is called entity linking. Well, it has multiple names. One hand, the dubbed name entity linking can also refer to named entity recognition, is what we saw before, and disambiguation. Classically, this is a three-step pipeline where you do mention detection, candidate generation, and then entity disambiguation here. So the idea is that we want to actually link our text to a knowledge graph. Some ways that can actually be done is by looking at co-occurrences, which is more of a statistical approach. And then you have other approaches which make use pretty heavily of BERT. And well, entity linking is strongly dependent on the knowledge graph because you might want to link to DBpedia or Wikidata and get different results. And well, one way that people also do is to check the distance from one entity to another within a knowledge graph, and then say, okay, these are closely related, so they should belong together within a sentence. But yeah, mainly it's ML approaches or, well, more neural network approaches nowadays. So down here, you have the typical entity linking pipeline, the more classical pipeline as you may have it. And here is a visualization of what this entity linking task looks like. This is the sample knowledge graph we had before. And as we saw before, NER was linking directly to the types. We are now instead linking directly to the entities. This green layer here is still the entities. And we want to figure out, okay, Tokyo in the text we had before was referring directly to the city, and sushi was referring to the food. Great. Now then, we'll go into the entity linking pipeline so that we understand the 3 steps of it. And so let's get into it. So we start with mention detection, which is the first part of this pipeline. We take an input document and we try to figure out what are the named entities within this text. So as we saw for NER, that was the underlining part of the task. And so oftentimes this step can also be performed by NER systems, but we don't really need the types for this here. It can be a subtask of entity linking or NER to be doing this mention detection, or it can just be to figure out, okay, what are actually mentions or what are actually spans in my document, and then just doing statistical analyses based on it. So it can also be a standalone task, but most of the time it's used for entity linking or NER. Now then, once we have our mentions or so-called spans, we can then figure out different candidates for them through candidate generation. So for a given span, we want to output a list of relevant named entities so that we know what could these spans even be to begin with. For instance, if we didn't have sushi food here and we just had like wrestler here, then it would kind of be hard to figure it out what we're referring to by sushi contextually for a machine learning system. So it's also important to have a good candidate generation system. And this here is honestly mainly used as a subtask of entity linking because that's the main use case that it's used for. So for Tokyo, we can find, as we had before in our knowledge graph, we can have the city, the film, the song, for sushi, the food, as well as the wrestler with the nickname of sushi. But we can also have different things, such as for temples that we had before, we can get temple, the structure, which is probably what we're looking for. Temple is apparently also university. You can also have it as a name. It's a surname, if I'm not mistaken, or it's part of your body. So how can we actually find these candidates? Well, actually, there's a few different ways, but the most simplest way would just be to, okay, we just search throughout. For instance, since these are all entries in Knowledge Graph, can just search for the so-called labels in Knowledge Graph and see, okay, is there some kind of text with temple in it? Or we can use a search machine, a search engine. So for instance, we have here the Wikidata website. Yay. If we go there and just search for temples, let's see what comes out. We have temples, which is apparently a website, blah. Then we have the singular temple that comes out, an English rock band. It's also apparently a family name, and so on. And depending on what kind of websites you're going for, you will get different results. Now let's see here, for instance, if we go for Wikipedia, what do we find for temples? We find, well, here it directly redirects us to temple, but there is also the simplification site, on Wikipedia where we see all the things it could actually refer to. It could be the Sky One television series or a movie and so on. Part of the head, like that's the body part or the anatomy aspect here. And so that's what we do in candidate generation. We try to just figure out what could this possibly be. Like, give me all the relevant options, because oftentimes there's more than one option. To us humans, it's obvious. To machines, less so, unfortunately. And so they might need more for you to actually give them more of the options, and then for them to try to figure it out from the context. Like if you write Tokyo and sushi, it might kind of be obvious, especially when you have this kind of more touristy context in it. And the sushi emoji there, for instance, like that would probably be a big hint to anyone, to any human reading it at least. So after we have generated all the candidates here that we want to have, that we want our systems to be able to see as a context, we then have to figure out which one is the correct one, and that step is called entity disambiguation. So the task in entity disambiguation is that given a list of named entities, you want to figure out which one is meant. Oftentimes it's a ranking algorithm where we attribute different kinds of scores to each candidate entity here, and then we figure out, okay, we just take the topmost one. And as such, we can filter out all the ones that are not relevant for our current use case. Now then, for entity linking, cool, there's some examples. Let's have a look at some of them. The first one we'll have a quick look at is called DBpedia Spotlight. It's not a particularly recent one, but it's pretty easy to use, pretty intuitive. They have default text here. Berlin is capital, blah, and so on. And then we can choose a different, whatever language we want. There's a certain degree of confidence that we can set. And then n best candidates, which then would give us also multiple candidates there. And then let's just do annotate. And then when we annotate it, we see that, okay, Berlin gets annotated. Berlin is then found to be DBpedia resource Berlin. Now then if we go here, cool. Nice, here we see this is the correct Berlin that we want to find out. It's not, it's the capital and the largest city in Germany, blah, cool. So that's a pretty, some would say it's a pretty easy example, but there's also other things that actually refer to by the name Berlin. Now let's look at Babelfy, for instance. Here, before I had, let's actually open up the site anew again and try to take some of that text we had from DBpedia. Let's take the first sentence, for instance, because otherwise it gets a bit long in Babelfy, because they visually try to make it pretty. There we go. So it's an English text, because you can do it multilingually as well. And here we have, for instance, Berlin is the capital and largest city of Germany. And in Babelfy, you can then see, okay, it's a provincial capital. When you say capital, but it didn't find Berlin itself. It finds the largest city. It did not find Germany. It found area and found population, which is interesting because it found those general concepts, but couldn't find Germany and Berlin specifically, which is very interesting to see. Because to a human, it's obvious that, okay, this and this here, you'd want to know what it's about. And here it's more, Babelfy was more focusing apparently on the more structural aspects of the sentence. Talking about, okay, this noun here means this other one means this. And so there's all kinds of differences between systems. And yeah, that's it. From the examples that we've had, we looked at now this entity linking pipeline in full, along with the topics of sentiment analysis, named entity recognition, and so on. And well then, with that, I wish you a lovely winter holiday. Bye.